Welcome to MathMuni. We are given this surprising looking problem mentioning that Julius Caesar, the Roman dictator, was assassinated about 2000 years ago. What are the chances, the question asks, that you have just inhaled a molecule which Caesar exhaled in his dying breath? Let's start by first taking stock of the data. The first assumption is that after more than 2000 years since Caesar's death, the molecules that he exhaled in his last breath are uniformly spread about the world, and the majority of them are still free in the atmosphere. We are also told that there are a total of 10 raised to the power 44 molecules of air in the world. And finally, every breath of inhalation and exhalation is about 1/30th of a mole. One mole has 6 into 10 raised to the power 23 molecules, the Avogadro number. So every breath has this many molecules divided by 30, which is equal to 2.2 into 10 raised to the power 22 molecules. Now, our first instinctive reaction to this question is that the chances that we just inhaled a molecule of air that was exhaled 2000 years ago by one individual in some faraway corner of the world, the probability of that happening is negligible. And sure enough, our first calculations support this intuition. The probability that a molecule we just inhaled was one of those exhaled by Caesar is equal to the number of molecules exhaled by Caesar, which is the favorable scenario, divided by the total number of molecules in the atmosphere of the Earth. So this is equal to 2.2 into 10 raised to the power 22 divided by 10 raised to the power 44, which is equal to 2.2 into 10 raised to the power minus 22. Therefore, the probability of the complementary event that this molecule we inhaled was not exhaled by Caesar is equal to 1 minus 2.2 into 10 raised to the power minus 22, which is approximately equal to 1. So far, so good. But remember that this is for just one molecule that we inhaled. Now, say for a minute, assume that we inhaled 2 molecules. The complementary probability that neither of these 2 molecules were exhaled by Caesar 2000 years ago is equal to the probability that the first molecule was not exhaled by Caesar multiplied by the probability that the second molecule was also not exhaled by Caesar. This is equal to 1 minus 2.2 into 10 raised to the power minus 22 multiplied by 1 minus 2.2 into 10 raised to the power minus 22 again. And this is equal to 1 minus 2.2 into 10 raised to the power minus 22 whole raised to the power 2. Now remember, we just inhaled not 2, but 2.2 into 10 raised to the power 22 molecules. So the probability that neither of the inhaled molecules was one of those exhaled by Caesar is equal to 1 minus 2.2 into 10 raised to the power minus 22 whole raised to the power, instead of 2, now we write the total number of inhaled molecules, which is 2.2 into 10 raised to the power 22. And this is approximately equal to 0.00791. And to our surprise, the probability that neither of the inhaled molecules is one of those exhaled by Caesar is actually very small. Contrast this with when we did our first calculation above. For one inhaled molecule, the probability that that one inhaled molecule was not exhaled by Caesar was nearly 1. Therefore, the probability that at least one of our inhaled molecules was exhaled by Caesar is equal to 1 minus 0.00791, which is equal to 0.992. So even though Caesar died 2000 years ago in Rome, his last breath is still very much around us. The surprising conclusion we have come to is that there is a very high chance of us having just breathed at least one molecule that was exhaled by Caesar in his last breath. So what did we learn from this problem? This problem is a classic example of the working of the multiplication principle in probability. Contrary to our initial intuition, the individual probabilities of a very large number of events can surprisingly stack up, even if those individual probabilities are very, very small. It is hard for us to trust our initial intuition when very large or very small numbers are involved. A systematic calculation, like the one above, is the only way to find out the truth. And what about the facts we have been given in the case about Caesar being assassinated 2000 years ago in Rome? Some of this information is irrelevant, like the fact that he was assassinated and that he was in Rome then. But some of the given information is there to help us simplify our assumptions. So in 2000 years, we expect the molecules from his last breath to have diffused almost entirely in the Earth's atmosphere, which means that regardless of whether you live in Rome or anywhere else on planet Earth, the probability of breathing any of his exhaled molecules can be assumed to be uniform, the same for all of us. So that's it. We have from this problem a useful reminder that the law of multiplication of probabilities can produce surprising outcomes, especially when a very large number of events are superimposed on very small probabilities. It is difficult for us to form a reliable intuition in such cases, so best to pursue a systematic mathematical approach. I hope you had fun, and I will see you back at MathMuni for the next story, where mathematics comes to our rescue and saves the day. Meanwhile, check out mathmuni.com for hundreds of mathematical problems across a range of topics. We are rapidly expanding our collection and would love to hear your feedback. Please drop your suggestions in the comments below. Bye for now.